If you ever wanted to understand the physics of small things, you might notice that something's wrong, that is strange and incorrect in terms of classical physics. One of such is wave-particle dualism. We know that electrons and atoms are particles. Just take a look at this. There is a cloud chamber and a radioactive element inside it. The chamber shows the trajectory of charged particles emitted from the material. And these particles leave trail of ions, and the steam inside the chamber condenses on them. This is certainly a trajectory of a particle, not a wave, right? Now, take a look at this setup for the double slit experiment. There is a wall with two vertical slits, and if we were to shine light between these two slits or shoot particles through it, we would instinctively expect to get two vertical lines. But instead, we get an interference pattern which results from an overlapping of two waves from each of the slits. Even by shooting electrons one by one, you get the same interference pattern. So it's a wave! No, the thing is, such small objects do not behave that simply. The wave nature represents a probability of finding a particle at the chosen spot. So the interference pattern we've got during our first experiment can be interpreted as a probability distribution. In places where waves add up, the probability is reasonably high, while in places where they cancel out, the probability is quite low. Scientists have made an experiment with buckyballs, huge molecules consisting of 60 atoms of carbon, and they have been shooting these microbullets in the setup and still saw the same interference pattern. In 1924, Louis de Broglie proposed that all particles with mass exhibit wave-like behavior and can be described as matter waves. It means that this occurs with every existing thing in our world. This formula describes the dependency between de Broglie wavelength and its momentum. Why does this not occur with big enough objects like a volleyball? Well, the bigger the mass, the lesser its wavelength, and including the fact that this Planck's constant value is just too small, we need the masses way more bigger than those of everyday objects. For instance, an average volleyball moving at speed of 100 meters per second will have the wavelength power of -34. In comparison, the radius of a hydrogen will still be bigger, although it's a very small atom and its power is just -12. This value is too small and the wave-like behavior is simply left unnoticed. So, a wave or a particle? Actually neither. Although they have both properties, we use this concept to describe different cases they might be in. For example, we presume it's a particle if we talk about interaction, or it's a wave if we talk about its motion through space. Scientists have developed mathematical models explaining their movement, and they can even make subatomic particles interact with each other. They can use it, but the question what's actually going on here is still left unanswered.